Welcome everyone to the last lecture in Module 12 and the last lecture for this semester. We're going to finish up by discussing diffraction. So in order to define diffraction, what we mean by this is when we send waves, in this case we're looking at light waves, through some sort of obstacle or narrow passage, which actually produces an interference pattern. Last time we looked at the case of Young's two-slit experiment, in which we were looking at two separate slits and how the waves that went through them interfered with one another. But now I'm changing it up on you a little and telling you that even with a single slit, you will end up with an interference pattern. And the reason for that may not be immediately obvious. So let's see if we can figure out why. When we talked about Young's two-slit experiment, we suggested that a plane wave was incident upon the obstruction where you had the two slits. The problem with that description is that plane waves are sort of an idealization. And to get a little bit more accurate picture of how you could think about what's going on here, we're going to invoke the Huygens principle, in which case we can think about each of these plane wave fronts as consisting of small little wavelets. And each of these wavelets then has the potential to interfere with one another. Thus, when I force them through this narrow passageway and redirect their direction, then the little wave fronts have the possibility of interfering constructively or destructively with one another. And so that's how we can get an interference pattern to occur even with a single slit. And sometimes this is just referred to, in fact, as a diffraction pattern. So like the two-slit experiment, we have an equation we can use to determine where the location of the bright and light fringes are going to be that are produced in a single slit interference. And it's a very similar equation. I'm just going to point out some differences for you. So if you read what's described here, this is the position of the dark fringes rather than the light fringes where we stick in these integer values. And then the other difference is that instead of the distance between the two slits when we had our two slits, that's no longer a sensible thing because we only have one slit. So we're using the width of the slit here as what goes in the denominator here. And of course, all of this can be derived. We're sort of skipping that derivation for now. Okay, for example, if I wanted to know where the location of this first dark fringe would be, I would plug in an n equal to 1 in here, and along with the width of the slit and the wavelength of light I was dealing with, that would tell me how far off of this line, sine of this line, is going to be where that dark fringe is. Okay, so for example, if you were trying to decide among some various slit widths for some experiment, the wider the slit width, what will that result in for the pattern of fringes that you see? Well, remember that sine of theta is going to be equal to n lambda over W. So for some given wavelength, then the more that I increase the denominator here, that's going to decrease this overall number. So the wider the slit, the closer together these, whoops, sorry, went the wrong way, these dark fringes will be. They will be closer and closer together until you get to the point where if you make the slit wide enough, you're not really producing any diffraction at all, and things just end up on top of one another, and you're projecting light onto some screen. Okay, so, but the idea of diffraction being that we're forcing light through some sort of narrow passage, this has been exploited for many applications. For you bio majors out there, the thing you might be familiar with is the X-ray diffraction, which was used to deduce the structure of the DNA double helix. That was done because using a wavelength of light in the X-ray band, it was just the right size to produce this diffraction pattern whenever it was shown through the DNA, and from that then the shape of the DNA was able to be figured out in the 1950s. Okay, and as you might suspect, forcing light through some sort of narrow passage doesn't always involve some nice rectangular slit. In fact, we may use circular apertures for different purposes, and light might be forced to pass through some circular slit instead. And when it does that, it will produce, again, some sort of interference pattern, but this is more of a circular interference pattern where it looks like a bullseye with a bright spot in the middle, and then rings working outward from there. And so there's an equation we can use to quantify this as well. And again, I'm not going to take the time to derive it, but the first dark fringe that you're going to see, or the first minimum, is going to occur at 1.22 lambda over d. Sine of theta will be equal to that. And so why does this matter to us? Well, what would happen if we had, for example, another light source that was close by and maybe its peak was something like this? If these things are too close together, you're not going to be able to tell or resolve that there are actually two different light sources involved. So even when light is passing through, for example, the aperture of your eye, your pupil, you may see two light sources apparently looking like one because you cannot resolve where this dark fringe begins from where this dark fringe begins. And so you may be, an everyday example that you may be familiar with is if you are driving down the highway and you see a distant car, if they're far enough away, the headlights sort of bleed together into one, and you can't really tell that they are two different light sources. Only when they get a little closer can you start to resolve that there are actually two separate headlights there. So the criteria that must be met for you to be able to resolve these things is that you need to be able to start to see this black dark fringe appear. And so you want for the sine of theta to be equal to 1.22 lambda over the diameter. You want to be able to make resolve that there are two different things even when this is small. The smaller this is, that means better resolving power. So that's really what I'm asking on this next slide here as a clicker question, which implies better resolution. So given this equation here, if the angular separation is actually very small, and I'm able to see where that dark fringe is, then I've met the Rayleigh criterion, and I'm able to achieve good resolution because I can tell that there are two separate light sources, even though their angular separation is small. I can toy with these other things on the other side of the equation to try to achieve good resolution. One of them is the wavelength, and the other is the diameter of the circular aperture. So some of those things may or may not be able to be changed. I may not be able to change the circular aperture size, or I may not be able to change the wavelength. A good example of that is if I am a radio astronomer. I can't change the fact that the wavelength of light I'm looking at is very large. So in this equation here, if I increase the wavelength here, I'm going to increase this left-hand side of the equation, meaning that the two perhaps stars that I'm trying to resolve need to be far enough apart for me to be able to tell that there are two of them there. The only thing I can do to try to counterbalance that is increase the diameter of my radio telescope in order to try to hope to bring down this overall right-hand side of the equation, which will then bring down the overall left-hand side of the equation and allow me to resolve things even if they are closely separated. And this is why you see radio telescopes being built that are enormous sizes. So here is an example of a radio telescope in West Virginia and some small humans for comparison. And this, by the way, is a modest sized radio telescope. Many are actually very large. And just to show you how embarrassingly old this picture is, here are the people involved now. Why don't we end with an example regarding this idea of a radio telescope and see if we can get a sense of what kind of angular separation is resolvable for a radio telescope. So this particular problem gives us an approximation to make. Whenever we're dealing with small angles, the sine of that angle could be equal to approximately that angle. So we're going to make that approximation, and we're going to see what the angular separation is that's resolvable for a radio telescope of a given diameter, which is tuned into a specific frequency. So given this equation on the previous slide, we're going to make the approximation here that sine of theta is equal to approximately theta. So theta is going to equal approximately 1.22 lambda over d. I've been given the diameter here, but I have not been given the wavelength. I've been given the frequency. However, just as in the last lecture, we can use this equation to solve for the lambda in terms of the frequency, and so I can replace lambda in this equation with c over f, and so that will tell me that the angular separation I'm looking at is going to be something like this. Okay, and if I plug in the speed of light, it's 3 times 10 to the 8, the frequency that was given to me, and the diameter, this turns out to be 0.122 for my answer, and this turns out to be approximately 7.3 arc minutes. Okay, which is interesting because the human eye has a limit of being able to resolve two things that are approximately 1 arc minute apart. An example of that you can look for in the night sky is if you look for the Big Dipper. In the handle of the Big Dipper, these two stars, Mizar and Alcor, are approximately 1 arc minute apart from one another in angular separation. And so if you look at them carefully, if you look at that point carefully, you can tell that there are actually two stars there. So what this example is saying to us is that even with a diameter of 30 meters, you do not get that great of a resolution in the radio end of the spectrum. You would need the stars or whatever objects you're looking at to be further away than something that you can already resolve by eye. So that means we really want to make our diameter of our radio telescope even larger than this if we want better resolution. Okay, and that concludes this lecture and all the lectures. I wish you the best on the final exam.